says a 25 centimeter cube sample of 2 molar hydrochloric acid was mixed with 50 of 1 molar sodium hydroxide. Both solutions were initially at 18 degrees C. After mixing, the temperature of the solution was 26.5. So immediately I can see that this reaction is exothermic. The temperature is increased. Use this information to calculate the standard enthalpy change for this reaction. Now, if you look at this reaction, you can see it's an acid reacting with an alkali. So it is a enthalpy of neutralisation. So an acid plus an alkali produces a salt and water. And it says, in your calculation, assume that the density of the solution, so the solution is this whole thing, is 1 gram per centimetre cubed. In other words, the density of the solution is the same as the density of water, because 1 gram of pure water has a volume of 1 centimetre cubed. Now, it's not a great approximation because obviously there's HCl in there, sodium hydroxide and salt being made, but it's okay for this type of level of calculation. And also the specific heat capacity is the same as that of water. So in the previous video, we were given the value for the heat capacity of water as C equals 4.18 joules per gram per degree C. Degree C and Kelvin are used interchangeably. As long as you stick with one unit, it's fine. So 4.18 joules per gram per degree C. I'm just going to do a little sketch of this setup to show you how it's different from the first part of this question that was actually drawn for us in the previous video. So what we have is a beaker and water with, let's call the acid A and the base B. A and B are both reacting in this solution and generating the temperature change. Okay, so we have this line, that's the thermometer, and we read the thermometer and notice that the temperature would increase to 26.5 because it's exothermic. A and B are both in the pot of water and the temperature change is being generated in the pot itself. This is different to the previous part of the question in the last video where we had a beaker of water and a fuel was burnt outside, so ignited, and then that generated heat and raised the temperature of the water. So they're just different setups. Okay, so this is why I've done a separate video on this. Next thing, formulas. So E equals mc delta T. M is the mass of the solution this time, because the solution is the same as water. So that is that. C is your heat capacity, delta T is your change in temperature, and then E is the energy released in the reaction. Right, there is another formula we need. Because we are dealing with solutions and not masses in grams, we need the moles formula for solutions, which is moles equals concentration times volume. So the concentration, for example, the HCl is there, always in moles per decimeter cubed. That's a standard unit. And the volume is must always be converted to decimeter cubed. 1,000 centimeter cubed is 1 decimeter cubed, which means those numbers have to be turned into decimeter cubed. Let's go and work out the energy. So E equals mc delta T. So therefore E equals the mass of the solution is 25 of the acid added to 50 is 70 times 4.18 times temperature change of 26.5 minus 18 gives us. Next thing we need to do is work out the enthalpy. And if you remember what I said in the last video, is the enthalpy change is the energy divided by the moles of the reactant. Well, in this case we have two reactants. We have this one and we have this one. So how do you know which one to use? Well, the answer is simple. You always use the moles of the reactant which has the smallest number, the one that is known as the limiting reagent. So you usually have one reactant which is in excess and the other one is in a smaller amount. So you always go with a smaller number of moles because that is the number of moles that will dictate the amount of product being formed, which in this case is sodium chloride, the salt. So how do I know which has the smaller moles, A or B? It's simple. I'm just going to work them out. So moles equals C times V. C is 2 Volume is 0.025. Remember, I've just turned it into decimally cubed, and that gives me 0.05 moles. Now let's do the same for the hydrochloric acid, with the sodium hydroxide, and that also gives 0.05 moles. So you will see the moles of acid and alkali are exactly the same, okay? And that's deliberate by the question, by the way. So it doesn't matter which one I pick for my final answer to work out this, because they're the same. But very common in other questions is you will find one moles greater than the other. So please remember, always take the smallest number of moles, as that is the limiting reagent, and that's the one that dictates the amount of product. We're going to have 2487.1 divided by 0.05. So I end up with 49742 joules per mole. Remember, the standard unit of enthalpy is always kilojoules per mole. So now I have to divide this by 1,000. So dividing that by 1,000 gives me 49.7 kilojoules per mole. And don't forget, minus sign must go in because it's an exothermic reaction. Energy is released to the surroundings, so enthalpies for exothermic reactions are negative. Link is down below for the next one, so please go and check that out now.